In the final lecture of this module, we want to focus on reaction mechanisms. Remember our representation of a generic chemical reaction where we wrote some reactants, A and B, go to products, C and D, and in the balanced reaction, there would be coefficients, which are in blue here. And when we first wrote out this generic chemical reaction, we put this reaction mechanism box in the middle, which we said was a series of elementary reaction steps. In this lecture, we want to concentrate on what we might find out about what's going on in this reaction mechanism box. So when we say we're going to look at the reaction mechanism, what we're really saying is that we're going to make intelligent guesses as to what's going on in this reaction mechanism box, and most importantly, how it relates to and actually determines the reaction rate and the rate law. Now, of course, we said before that we determine the rate law experimentally and the reaction rate experimentally. But when we do that, what we're looking at is how fast the reactants go in this box, or how fast the products come out of this box as a function of the reactant concentration. So we can establish the rate law and the reaction rate experimentally, but what we don't know is really what's going on in this box. And so we're going to make guesses about what's going on in this box, and our guesses need to be consistent with what we've determined as the experimentally determined rate law and reaction rate. So a reaction mechanism is simply a proposed series of single-step reactions, and by single-step reactions, we mean elementary reactions, and events such as collisions, bond breaking, bond formation, occurring at the molecular level to form a pathway that transforms reactants to products. Now let's consider the following reaction, which is simply nitrogen dioxide reacting with carbon monoxide, CO, to form nitrogen monoxide, NO, and carbon dioxide, CO2. You can see what's going on here overall is that an oxygen atom is being transferred from NO2 to CO. Now the rate law experimentally has been determined to be rate equals K times the concentration of NO2 squared. So experimentally, this reaction shows no dependence on the concentration of CO, but a squared dependence on the concentration of NO2. If we rewrite this reaction, including the reaction mechanism box, it would look like this. Here's our reactants, NO2 and CO. Here are our products, NO and CO2. We'd like to make some guesses as to what's going on in this box to go from reactants to products, and our guesses need to give us a rate law that's consistent with what we find experimentally. So I'm going to expand this box so I can write in it, and we're going to propose a reaction mechanism, and our reaction mechanism is going to be a two-step reaction mechanism. In step 1, we are going to propose that two NO2 molecules collide with each other and form something called NO3, or at least with the formula NO3, and NO, and that this is a slow step. And in step 2, the CO, which we seem to ignore in the first step, reacts with what was formed in the first step, NO3, to form NO2 and CO2, and we'll say that this is a fast step compared to the first step, which we say is slower, so we call it the slow step. The slow step in a reaction mechanism has a special term. We call it the rate determining step, because the overall reaction from reactants to products cannot go any faster than the slowest step in the reaction mechanism. Now, this proposed mechanism is valid. Now, I'm not saying that it's the correct mechanism, but it's a good guess, so we're going to say it's valid for two reasons. One is that these two steps correctly add up to the actual overall reaction. By the overall reaction, I mean we're stating that NO2 plus CO has to go to NO and CO2, and this mechanism adds up to that overall reaction. And secondly, it correctly predicts the experimentally determined rate law. So this reaction mechanism predicts that rate should be a function of the square of the NO2 concentration and should have no dependence on CO. Now, you might ask, how do we know that? Well, let's try to unpack this on the next couple slides. Let's look at the first reason why I say this is a valid mechanism that we proposed. We said it correctly adds up to the actual overall reaction. And what we mean here is that if we simply add up the two elementary reaction steps in our mechanism, steps 1 and 2, we will get the exact same reactants and products as seen in the overall reaction. So let's write our proposed mechanism again. Here's step 1. Here's step 2. And what we're going to do is add these two reactions together. Now, what I did here was I simply added up everything that's on the left of the arrows, NO2 plus NO2, and then NO3 plus CO. And then on the other side of the arrow, I added up everything from these two reactions above that are on the right side of the arrow, NO3, NO, NO2, and CO2. We then can simplify our overall reaction here, and the first thing we could do is combine some like terms. So there's two NO2s on the left of the arrow, so let's just rewrite it as 2NO2. We rewrite everything else, and then we look and say, hey, there are some things that are the same on both sides of this chemical equation, and so we're just going to subtract out things that are the same. There's an NO2 on this side, and there's 2 on this side. I'm going to subtract 1 from both sides, and now we're left with this equation. And then there's an NO3 on each side, so I'm going to subtract those out. And what we're left with is NO2 plus CO going to NO plus CO2, which is the overall reaction that we're dealing with in reality. So our two-step reaction mechanism has passed its first step, its first test, I should say. It correctly adds up to the actual overall reaction. Now, what we've done here is we've treated chemical equations like equations in algebra class. The arrow is equivalent to the equal sign. You might ask, isn't there a faster way to add equations together and cancel out terms or combine terms? And yes, there is. So let's just look at this again on the next slide, and we'll try to be a little more efficient. So here's our goal, that our proposed mechanism add up to this reaction, and we'll write out our 2 steps for our proposed mechanism. And what I did here was I simply canceled out terms that are the same on both sides of the arrows. So here's an NO2 on the left side of an arrow up here, and here's an NO2 on the right side of an arrow down here, so I canceled those out. Here's an NO3 on the right side of an arrow up here, which I canceled with an NO3 on the left side of the arrow down here. And then we add up everything that's left, and we get the overall reaction, which is what we wanted. We wanted it to be equal to or the same as the actual overall reaction. So you can see this is a little quicker way to add up reactions. Now, our proposed mechanism must still pass the second test. And remember, the second test is that it should correctly predict the experimentally determined rate law. The experimentally determined rate law was that rate is a function of the square of the NO2 concentration and has no dependence on the CO concentration. So we reproduced our proposed mechanism down here. I re-added the information that the first step is the slow step or the rate determining step, and the second step is the fast step. And I added a couple of extra labels. So the reaction in step 1, which we labeled the slow step, we'll say has a rate constant equal to K1, and I write it over the arrow. You've seen this before in a previous lecture. And the reaction in step 2, which we labeled the fast step, has a rate constant of K2 for reaction 2. And since we have assumed that the reaction in step 1 is the rate determining slow step, we can also assume that the rate constant for step 1, K1, is going to be less than the rate constant for step 2, K2. Okay, so what now? Well, both step 1 and step 2 in the reaction mechanisms are defined as elementary one-step reactions. I've said this more than once, and you might ask why this is important. It's important because for an elementary one-step reaction, which you know is a one-step reaction, we can actually write an individual rate law for each reaction. Let me show you what I mean. Here's again our proposed reaction mechanism. And across from step 1, I've written a rate law for step 1. I've said the rate law for step 1 is we say rate of step 1 equals the rate constant for step 1 times the NO2 concentration squared. I'm saying that because there's two NO2s here. And we're basically adding up these coefficients and putting them right there. For step 2, we have NO3 reacting with CO, and so we can write a rate law for that reaction. For step 2, the rate of step 2 equals K2, the rate constant for step 2, times the first power of the concentration of NO3, because there's a 1 in front of the NO3 here, a coefficient of 1, and the first power of CO, because there's a 1 in front of the CO. Now I'm hoping you're going to object to this, because we were very careful to say earlier that you cannot simply write a rate law straight from a balanced reaction. However, that was for a reaction that we could not guarantee was a one-step reaction. Because remember, all the reactions we've looked at before, we had reactants going into a reaction mechanism box going to products. So we can't say that the reaction went specifically from reactants to products in one step. However, for an elementary reaction, which is what's defined as what's going on in this reaction mechanism box, it is valid to write a rate law directly from the chemical equation. So elementary reactions are defined as one-step reactions. Therefore, we can write rate laws directly from those balanced equations. Now, we're not done yet. So let's rewrite everything we have here, and we're still on this point of showing that the proposed reaction mechanism predicts the experimentally determined rate law. Now, since the rate determining step, this is the first step, the one that controls the overall rate of the whole reaction, has a rate law which is identical in form to the experimentally derived rate law, this proposed mechanism is valid. In other words, this proposed mechanism passes our second test. Again, since step 1 is the rate determining step, it determines the rate of our overall reaction. And step 1 has a rate law written from this elementary reaction, which is of the same form as the experimentally determined rate law. Then we say this is a valid reaction mechanism. So here's our experimentally determined rate law. Here's our rate law that comes out of our proposed mechanism. They are both of the same form. They both show rate as a function of the square of the NO2 concentration and show no dependence on the concentration of CO. So in summary, our proposed mechanism for this reaction is a valid guess because it correctly adds up to the overall reaction, and it correctly predicts the experimentally determined rate law. Now, what about the rate law for step 2 in our proposed mechanism? Well, we don't use the step 2 rate law expression since step 2, being the fast step, is not the limiting factor in determination of the overall reaction rate. What about CO, the other reactant in the overall equation? Well, remember, the experimentally determined rate law shows no dependence on the CO concentration. Our proposed mechanism explains this lack of dependence on the CO concentration. Our proposed mechanism says first, the collision of two NO2 molecules, which is a slow step and determines the overall reaction rate, must occur. Then the fast reaction of CO with one of the products of the initial collision of those two NO2 molecules occurs. So CO, of course, is part of the reaction, but it doesn't determine the overall rate of the reaction. Its concentration does not, and our mechanism explains this. So let's summarize some useful information about reaction mechanisms. First of all, a reaction mechanism is a proposed series of elementary single-step reactions that attempts to describe on the molecular level the pathway or pathways that are taken to get from reactants to products. To be valid, a reaction mechanism needs to contain elementary reactions that add up to give the overall reaction and predict a rate law that matches the experimentally determined rate law. The rate determining slow step in a proposed reaction mechanism is the starting point for using that proposed reaction mechanism to derive an overall rate law with the goal of matching the experimentally determined rate law. I put a couple of asterisks after the elementary single-step reactions to make you aware that there is some terminology associated with these. A unimolecular elementary reaction is one involving only one molecule. A bimolecular would be an elementary reaction involving the collision of two molecules, and a termolecular would be an elementary reaction involving the collision of three molecules. Now, most elementary reactions in proposed reaction mechanisms are either unimolecular or bimolecular. Termolecular reactions, the collision of three molecules together, is statistically not very significant, but it is proposed in some reaction mechanisms. Now, both elementary reaction steps in steps 1 and 2 of our proposed mechanism for the reaction of NO2 with CO involved bimolecular reactions. You might want to note here that, interestingly, a proposed reaction mechanism, even if it meets the above requirements, which ours did, can never fully be proved. It is possible that there are other reaction mechanisms that could be proposed that meet the same criteria. Chemists that study reaction kinetics many times devise clever experimental methods to disprove some proposed mechanisms. Now, if a reaction mechanism cannot be disproved for a long period of time, no matter how hard people try, that eventually becomes the accepted mechanism, until, of course, someone finds a way to disprove it. Let's take a little closer look at reaction mechanisms. Let's look at this reaction that we've talked about a lot here, our overall reaction of NO2 with CO. We have our experimentally determined rate law. We have our proposed mechanism. One thing I want to point out here is that, as we've said previously, both steps 1 and 2 here in our proposed mechanism involve elementary reactions that are bimolecular, the collision of two molecules. A new term that we want to introduce here is calling NO3 in the reaction mechanism an intermediate. This is an important term in reaction mechanisms. You'll notice NO3 appears as a product in step 1, but then it's quickly used up in step 2. So it appears and then is rapidly used. So it's called an intermediate. Now, how does one know what intermediates are reasonable to propose in a reaction mechanism? Well, a chemist needs to learn from experience what intermediates are reasonable to propose. That may not be a very good answer, but that's the best one I can give you at this point. Let's take, again, a closer look at reaction mechanisms. You can construct a qualitative energy diagram of a proposed reaction mechanism. And we've done this before, but we'll look at this in a little more detail. The overall reaction that we've looked at, of course, is this, with the overall experimentally determined rate law here. And here's our proposed mechanism. And remember, step 1 is our slow step. So what we're going to remind you here is that this first step has a rate that's governed by an activation energy, and we're going to call it EA1 because it's from step 1. And step 2, the rate would be governed by a different activation energy, which we're going to call EA2. And in this case, the activation energy for step 1 must be larger than the activation energy for step 2 because step 1 is the slow or rate determining step. Now we can map this out with an energy diagram. So let's look at this in pieces. Remember, we have energy on the y-axis and reaction progress on the x-axis. We have reactants here, NO2 and CO, and we have products over here, NO and CO2. This particular reaction is exothermic. We'll get back to that in a second. So the products end up at lower energy than the reactants. But more importantly, what I want to show you is that we have this double hump here because the reactants go over the first activation energy in step 1 and form our intermediates, NO3 gas. Now I've called NO an intermediate here. Technically it's not an intermediate, but this certainly is the product of the first reaction, step 1. And then these two then, of course, don't react together to form the product, so it was hard for me to draw that here. NO3 then reacts with CO to form NO2 and CO2. The point is, step 1 goes over an activation barrier of EA1 and forms some products, and then step 2 occurs and it goes over reaction or activation barrier EA2, and EA2 is smaller than EA1. So this step 2 is faster, and you finally form the products NO and CO2. Step 1 is the rate determining step, and so therefore has a significantly higher activation energy than step 2. Now the overall reaction does turn out to be exothermic. Delta H is negative, and some textbooks may refer to this energy difference as a negative delta E rather than a negative delta H. Let's talk about catalysts in reactions. Before we talked about, in a previous lecture, about increasing reaction rates by increasing the temperature. Sometimes we don't want to increase the temperature, but we'd like the reaction to go faster, and we can do that by adding a catalyst. So we say a catalyst is a substance that increases the rate of a chemical reaction without itself undergoing a permanent chemical change. It can take part in the reaction, but it survives in its original form when the products are formed, so it can go on to catalyze more reactions. Now let's look at an example of a reaction that's catalyzed. A couple of decades ago, it was discovered that a common class of compounds called chlorofluorocarbons, used as refrigerants in air conditioners, when released into the atmosphere, eventually interacted with sunlight to produce chlorine atoms, which went on to catalyze the decomposition of ozone in the upper atmosphere. Now, we can write the initial reaction of a typical chlorofluorocarbon. This one was commercially named Freon 12, with photons of light to form a molecule that's missing one chlorine atom, and this chlorine atom is broken off by the photon of light and is now free. Well, what is this chlorine atom going to do? This can now catalyze the decomposition of ozone. Well, how would that occur? Well, a proposed mechanism for this, with Cl acting as a catalyst, is shown below. It's believed that in step 1, a chlorine atom formed from the interaction of light with the Freon 12 can interact with an ozone molecule to form chlorine monoxide and an oxygen molecule. Then the chlorine monoxide can find an oxygen atom, which also exists in the upper atmosphere, to reform a chlorine atom and form another oxygen molecule. And so the overall reaction here is that oxygen reacts with ozone to produce oxygen atom reacts with ozone to produce oxygen molecules. Now you say, so what? What's so bad about producing oxygen? Well, the ozone is being reacted. In other words, you're losing ozone, which is what we want to keep in the upper atmosphere. Now, this mechanism has both an intermediate and a catalyst. The chlorine monoxide here is an intermediate because it appears in step 1 and is used in step 2. And if we want to write the overall reaction, we would cross that out because it appears on the right of the arrow up here and the left of the arrow here. And the chlorine atom produced in this first reaction of the Freon 12 with light is the catalyst. It's used in step 1, in other words, it participates in the reaction, but in step 2 it's spit back out in its original form, so it can move on to catalyze other reactions. So I'm going to cross that out because it occurs on the left of the arrow here and the right of the arrow here, and that gives us our overall reaction for the decomposition of ozone. The decomposition of ozone involves an oxygen atom, but the reaction is catalyzed. In other words, it's sped up by the catalyst, chlorine. Now this is an example, chlorine here is an example of a homogeneous catalyst. And a homogeneous catalyst is one that's in the same phase as the reactants. In this case, the catalyst is in the same phase, the gas phase, as the reactants, oxygen and ozone. Now remember, a catalyst increases the overall rate of a chemical reaction. It does this by providing an alternate reaction mechanism with lower overall activation energy. The alternate reaction mechanism is the proposed mechanism on the previous slide that involved the chlorine catalyst. So here's an energy diagram. that would describe both the uncatalyzed and the catalyzed reactions. Let's look at the black line here. What we say here is that this black pathway shows the activation energy for the net overall reaction of oxygen reacting with ozone to form two oxygen molecules. That would be the decomposition of ozone that does not involve catalysis by chlorine atoms. And you can see the activation barrier is really high, which means that even though the overall reaction is exothermic, that the reaction would be very slow. So ozone decomposition is not a huge problem in the upper atmosphere until you introduce chlorine atoms. The chlorine atoms catalyze the reaction in a two-step mechanism, and what we've done here is we've said, okay, the catalyst, chlorine, provides an alternate pathway. It's a double humped pathway with the first reaction being the slow step, the higher activation energy, at least that's what we're assuming here, and the second reaction being the fast step. And irregardless, you can see that the catalyzed pathway, the pathway that's the reaction mechanism that results from the addition of chlorine atoms, has vastly lower activation energies. So now oxygen and ozone turn into oxygen molecules much faster because of the catalyzed pathway provided by the chlorine atoms. And again, the overall conversion of oxygen and oxygen atom and ozone to oxygen molecules has a negative delta H or a negative delta E, if that's what you want to label it. One thing you might want to note here is that both the catalyzed and the uncatalyzed pathway have the same overall energy change. In other words, no matter which pathway you take, you're starting from the same reactants, oxygen and ozone, and ending up with the same products, two molecules of oxygen. So whether you get there quickly in the catalyzed pathway or very slowly, the uncatalyzed pathway, the overall energy change is the same for both. Now recall the catalyst on the previous slide. Chlorine would be a homogeneous catalyst or a homogeneous catalyst because it's in the gas phase and all the reactants and products are in the gas phase. A heterogeneous catalyst is a catalyst that's in a different phase than the reactants. Now, an example of a heterogeneous catalyst would be finely ground solid containing some metals like nickel, palladium, or platinum, which can act as what we'd call a catalytic surface upon which a reaction can take place. The reaction that we're interested in looking at is the reaction of hydrogen gas with ethylene to form ethane. Now, in the absence of a catalyst, this reaction is annoyingly slow. Let's look at the reaction that we'd like to catalyze in a little more detail. We have hydrogen gas, we have ethylene, it has a carbon-carbon double bond, and we'll put the catalyst over the arrow, and the product we want to get here is ethane. If you were taking organic chemistry, you would call this reaction the addition of H2 to the carbon-carbon double bond to form ethane. Now we can view the reaction mechanism and the metal surfaces catalyzing the reaction in the following way. Both hydrogen and ethylene molecules can adsorb on the metal surface. Now, first of all, note we're using the word adsorb with a D rather than absorb with a B to indicate sticking to a solid surface. And we simply say that hydrogen molecules have some sort of special interaction with a metallic solid, and we say the special interaction or interaction is shown with this dotted red line. And we say the same thing for ethylene. So we've, in a sense, through adsorption, anchored hydrogen and ethylene to the metal surface. The metal surface, of course, being the catalyst. Now, the interaction with the metal surface causes the hydrogen-hydrogen bond, that single bond, to break, resulting in two single hydrogen atoms adsorbed individually on the metal surface. And simultaneously, the double bond in the ethylene is being what we call activated by its interaction with the metal catalyst. We'll continue this on the next slide. Now, the adsorbed hydrogen atoms are thought to be capable of migrating from site to site on the metal surface, and as they do, they approach an ethylene and can add one at a time to the activated ethylene. So you notice in my little cartoon here, one of these hydrogen atoms has moved and added to this carbon-carbon double bond. And of course, this could happen again, and now both hydrogens have added to the carbon-carbon double bond, and we now have ethane, our product, that's still adsorbed on the metal surface. And then in the last step, we say the ethane product desorbs from the metal surface. And we can show that like this. And now the surface of the metal catalyst is free to absorb fresh hydrogen and ethylene reactants. Now, what we're saying is that this is our proposed mechanism for the catalyzed pathway, the lower activation energy pathway, for the conversion of hydrogen and ethylene to ethane, because in the presence of these catalysts, the reaction occurs much faster. So these metal catalyst surfaces, these heterogeneous catalysts, must be providing lower activation energy pathways for hydrogen and ethylene to form ethane. Now, in a similar fashion, the catalytic converter in your car contains solid metal particles that catalyze, among other reactions, the reaction of carbon monoxide and unburned hydrocarbons with oxygen to form carbon dioxide and water that exit from the exhaust gas. So these reactions that are occurring on the surface of metal particles in your catalytic converter, also an example of heterogeneous catalysis. Finally, let's take a brief look at catalysis in biological systems. If you recall from high school biology class, enzymes are considered to be proteins that act as homogeneous catalysts in living systems. Recall that homogeneous catalysts are catalysts that are in the same phase as the reactants and products. In our previous example, everything was in the gas phase, the reactants, the products, and the catalyst. In this case, in a biological system, of course, they're all dissolved in aqueous solution. We can use a generic two-step reaction mechanism to describe the functioning of an enzyme. The enzyme is represented by E, and it's catalyzing the transformation of some reactants, which in this case we call substrates, to products P, and that two-step reaction mechanism has a fast step. So the first step is considered to be the fast step, where we form an enzyme substrate complex, and the second step is considered to be the slow step, and of course that's our rate determining step. If we crossed out the enzyme substrate complex, which is an intermediate that appears and disappears, and the catalyst E, as we've done in previous mechanisms, the overall reaction is this kind of simple looking substrate going to product. If you're concerned here about the double arrows in step 1 in this fast step, this is something that we'll see more of in the next module on equilibrium. But briefly here, what we have is a rapid equilibrium forming here. But the bottom line is that this first step, the formation of the enzyme substrate complex, is considered to be the fast step. The forward reaction has a rate constant K1, so we put K1 over the arrow going from left to right. The reverse reaction, which when it occurs, would be the enzyme substrate complex falling apart and going back to enzyme plus substrate, not forming product, would have a rate constant K minus 1. In any event, the important thing to remember here, or one of the important things, is that in general, one specific enzyme catalyzes one specific reaction. And that specificity of an enzyme is related to the 3D structure of what's called the active site of the enzyme. So here's a pretty good cartoon of what's going on here. If this gray blob here is considered to be the protein, the enzyme, with its active site, that active site is just the right shape to take two reactants in this case, two substrates. And so we have enzyme plus substrate, which quickly forms an enzyme substrate complex where the substrates are kind of tucked in this active site, but they haven't reacted yet. And then in a slow step, the enzyme facilitates the reaction of the substrates to form product, and then the product's released. So we have enzyme free to catalyze more reactions, and the product P is released. Now, again, decades ago when I took high school biology, we called this the lock and key concept, where the enzyme and substrates are perfect fits for each other. Prevailing wisdom now is that it's not quite that rigid. The enzyme can actually undergo some structural changes, and so to accommodate the substrate. So we might think of it more as an induced fit when the substrates approach the enzyme.